I'll get started with some of the work that we've been doing as a part of CBRIC on re-engineering computing with spike-based learning. I'm going to be talking about mainly the training algorithms, inference, and then time permitting. I'll also talk about the architecture and some of the neuromimetic devices that we've been looking at. I'd also like to acknowledge my students, the contributors, without whom, of course, this work would not have been possible. Now, to get started, we all know that deep learning certainly has made a huge amount of progress in the recent past. And AI certainly is scaling across applications. That includes image analytics, medicine, transportation, customer care, you name it. And AI is also scaling across investments and people, as is quite evident from the number, the course enrollment that we have, the number of courses, the course enrollment in AI, the number of papers which have been submitted in some of these conferences, in the AI conferences, of the order of about 8,000, 9,000 papers. And finally, certainly, it's scaling in terms of VC funding also, and that is also skyrocketing. However, if I really look at AI, there are several challenges that we have to overcome. If I look at the AI compute demand, and in this particular case, I'm actually looking at some of the machine learning computational cost over the years, and on the y-axis, I'm plotting the zeta operations, or in other words, the number of operations required, for example, to do network architecture synthesis. That's of the order of about 5 to 10 zeta operations, and that's a huge number of operations. So if I correspondingly look at the estimated CO2 emission from NAS on transformer, turns out it's about 315x higher than air travel from New York to San Francisco per passenger. So that's humongous. Now, if I then look at technology scaling, and we'll look at the scenario over there, that looks quite interesting and bleak in some ways. Dennard scaling has ended, and if you look at the general purpose systems, they have heater performance or energy bottleneck. Partially that comes from the fact that there's a von Neumann or the memory bottleneck that we have to deal with. So to that effect, there's a need for really thinking about domain-specific accelerators, and that's potentially going to be the key in all the future machine learning applications that we can be looking at. Now, going a little bit further and looking at edge intelligence, and if I look at the efficiency gap that exists today in AI, that's also quite large. So we looked at a case study doing object recognition in a smart glass with a state-of-the-art accelerator. In this particular case, we looked at the Google Edge TPU implementing RetinaNet on a smart glass, and it can be used for object detection and recognition. And what we found is kind of interesting that without going into the details, it turns out that the battery life for implementing that RetinaNet DNN on a smart glass, the time to die for the battery is actually under ideal conditions, just about an hour. Now, interestingly, that's ideal conditions, and if you really consider non-idealities that is going to really exist in real-life implementation, it turns out that the battery life is going to be probably half an hour or less. And that says a lot, and that certainly is not sustainable. You have to, changing battery every, half an hour or so. Now, the question, of course, is where do these inaccuracies come from? And these inefficiencies come from various levels of design abstraction. First of all, algorithms, the kind of algorithms that we're using probably are not, gives you energy efficiency. The hardware architecture which are implementing some of these algorithms are also not efficient. And finally, at the end of it, when you're looking at some of these neural networks, the circuits and devices that we're using are still CMOS based, and they are certainly good switches, but may not efficiently implement neuron and the synaptic functionalities. So to that effect, there's a need to really think about coming up with techniques to reduce this energy efficiency gap, and that would require that we look at the entire stack, going all the way from design stack, going all the way from learning algorithms and network architecture to the circuits and devices. Now the question is, in order to efficiently implement them, and since we're using, brain inspiration, in a lot of ways, the artificial neural networks or the analog neural networks that we've been using in deep learning, they're also inspired from the brain. So the question, of course, is, and at least we have an existential proof that the brain is efficient. So the question is, can we take more cues from the brain? So what are the different cues that we can, additional cues that we can take from the brain to make things efficient? And again, also remember something that we're looking at taking cues from the brain, looking at bioplausibility. And in all these cases, the bioplausibility is really a means to an end for learning, better algorithms, better learning techniques, or in fact, having better energy efficiency. So with that in mind, what we're going to be doing is looking at the brain and see if there are better neuron models or more exciting neuron models that we can use for better learning. What are the different learning algorithms that we can use? What kind of network topology is interesting? Can we use a network topology which is similar to potentially the visual ventral system? And finally, what kind of computing principles that we should use? So going into a little more details of it, the neuron models that one can potentially use could be the discrete spiking neuron models like leaky integrate and fire or integrate and fire neurons, or stochastic neurons. Stochasticity certainly has been observed in the brain, and so we'll see later on that using stochastic neurons potentially can give you advantages in terms of weight efficiency and so on. Or can we go and use more complex or more bioplausible models like the Hodgkin-Huxley model? From the learning algorithm point of view, the question is, should we use localized learning? Localized learning like spike timing dependent plasticity. I'll go into that in a little more details in the next few slides. Is that efficient? Can we apply such STDP-based learning to large-scale networks? That is yet to be determined. We can certainly use backpropagation, and backpropagation certainly has been used in the standard ANNs, and with some modifications, we might actually be able to use that in sort of spiking networks and so on. On the other side of it, what kind of network topology is good? Should we have recurrent connections? Should we have residual connections? Are these networks like brain-like networks? And if it is, do we have an advantage? Those are the other things that we need to look at. And then finally, looking at the computing principles, and that certainly includes, should I do communication and computing with spikes? And that's something that we can be focusing on today. Should I have a tightly integrated compute and memory, which is sort of in some ways in the brain, we end up doing computing in the memory itself directly. Should the computation be asynchronous, event-driven? And finally, and very importantly, we need to also look at what kind of input coding should we use. If I'm using, for example, spike-based computations, the input coding turns out to be quite important. Should it be rate-based coding? Should it be time-based coding? Or should we use, for example, for video applications and so on? Should I use DVS or camera inputs? I'll go into more details of each of those coding techniques and in a lot more details a little bit later on. So with that in mind, just to get started, I wanted to I wanted to mention that I'm not going to be talking much about the network architecture part of the work that is being done at CBRIC at MIT in Jim DiCarlo's lab. What they're doing is they're doing measurements on the monkey brain, where they're looking at the ventral system, the system of the monkey, the visual ventral system of the monkey, looking at V1, V2, V4, and IT regions of the brain. And they are actually probing these different areas of the brain to look at the activities that are going on when you show something, an image, let's say, to a monkey. And based on that, they're coming up with what's called a brain score. So with that brain score in mind, what they're trying to do is trying to come up with an architecture, which is shown on the top, which is could be a ResNet, could be a VGG kind of architecture, where the idea is to really match the measurement results which are coming from the monkey and try to match it or to have similar kind of brain scores, so to say, as is obtained from the monkey visual ventral system. To that effect, they've been actually able to come up with different kinds of architecture, an architecture called CoreNet, which has good accuracy while still being having a large brain score. And more recently, they've been actually looking at another kind of net, which is actually V1 net, which tries to implement the V1 of the visual ventral system of the monkey. And what they found is that actually that gives you better kind of robustness. I'm not going to go into the network architectures which are being designed after the the primate ventral system. So what I'm going to really focus on more is on bio-inspired encoding and computing. And to that effect, what we're going to be looking at is deep spiking neural network. Note the network structure that we're using, and the network architecture can potentially be a CoreNet or a V1 net, but they can be spiking. So we're not limited to a particular network architecture. So to that effect, we are looking at different kinds of training techniques using spike-based learning. I'll go into more details of that. Now, certainly for each of those networks, there's a need to really think about what kind of spike encoding that we do. As I mentioned, one can use rate encoding or time-based encoding, or in some cases, we'll see that the direct analog inputs coming from the pixels can potentially be used also for these spiking neural networks. And then finally, at the end of it, for all these networks, there's a need to think about what kind of spiking neuron model that we use. Should we use an integrate and fire kind of models? And we'll see for some of these analysis, or at least the learning techniques that we do, we use integrate and fire and leaky integrate and fire kind of models. And then we also came up with training techniques with stochastic switching of these neurons. And I'll go into more details of the neuron models in this slide. So to start with, I'm really showing a biological neuron. And if I were to model this biological neuron in a simplified way, a bunch of spikes come into this neuron. And as the spikes come in, the membrane potential of this neuron goes up. And if there are no spikes coming in, then there's a decay in the membrane potential, as you can see. And then there are a lot of spikes that are appearing. Turns out that the membrane potential goes up. And beyond a certain point, when it reaches a threshold, which is a threshold of this neuron, the neuron spikes, and then it goes into a state called the refractory period, when the membrane potential goes to close to zero, and it stays there for a little bit of time. And after that, it again starts behaving as a standard neuron, as I've shown in the figure. This can certainly be represented using an RC circuit, and the LIF equation for that RC circuit can be represented as I'm showing in that in the slide. Now, the neuron that I showed here is a leaky integrate and fire neuron. Now we can also think of a little bit simpler neuron model, which doesn't have that leak part to it. So if I don't have the leak, the neuron functionality looks somewhat like this, which is shown on using the red curve. And there's no leak in that particular case. And also this neuron, as you can see, would be spiking a little more than the leaky integrate and fire neuron. Now, there are certain advantages of using, leak, and one can show that, leak potentially gives a little bit of better generalization. On the other side of it, it's also possible to use neuron functionalities to be a little bit different. In this particular case, I'm showing a stochastic neuron. In an ANN, people use ReLU as the activation function for the neuron, or sometimes they use actually sigmoid or tan hyperbolic as an activation function. So in this particular case, I'm actually using a sigmoid as an activation function, but the sigmoid is a stochastic sigmoid, or in other words, the neuron would actually end up taking a value of, either it has switched or not switched, 0 or 1. And so the curve that I'm showing here is a probability that a neuron switch based on the input, which is shown on the x-axis that comes in. So in other words, the neuron is always going to have a value of 0 or 1. And so it also is considered to be a spiking neuron. Now, let's switch gear a little bit and talk about synapses. So as I mentioned earlier, the neuron is, let's say, a leaky integratin 5 neuron. And so what has been observed in the hippocampus of rats is a learning called spike timing dependent plasticity. And this was actually observed back in 1998 by Bo and Pai. So I'm going to use that kind of learning for that kind of localized learning in this particular case. So let's consider an example of that. Let's assume that there are 3 neurons, input neurons, which are I1, I2, and I3. And there's an output neuron O1, which are connected using these weights W1, W2, and W3. Now let's assume the case when I have a bunch of inputs which are coming in. In this particular case, I have 2 inputs, I1 and I3, and the output in this particular case switches. The output neuron switches and it has a spike which is shown in red. Now, interestingly, if you observe what has happened here, the output spike possibly occurred really due to spike at coming from I3. That played a major role. So in other words, if you look at a time difference between the spike coming from I3 and O1, that time difference is T, which is less than the spike that came from, or which is less than the spike that came from I1. Or in other words, the spike timing difference between 1 and the O1 is larger than I3 and O1. So in other words, if I were to now look at synaptic updates and looking at potentiation of synapses, then of course I3 did play a more important role. So looking at the time difference, what one can do is update the synaptic weight due to W3, and that is going to be more updated than, for example, the one which is due to coming from I1, since the timing difference is larger. And this kind of weight updates is called spike timing dependent plasticity. And so what you end up doing is the new weight for the new W1 and W3 are given by the old weight plus some delta W, and delta W is a function of some T pre minus of these neurons. Now if you have I2 produces a neuron which comes after the output O1 has fired, then of course that particular switching did not play a role in the output switching of O1, and hence in this particular case we actually depress the synaptic weights as shown there. So this kind of Hebbian learning has been sort of observed in the hippocampus of rats, as I mentioned, and can potentially be used for localized learning, as we'll see later on. Now, this kind of localized learning, as we'll also see later on, is applicable to probably smaller scale networks. It's difficult to apply to larger scale networks. So to that effect, there's a need for large scale networks that really need to think about backpropagation. And so backpropagation certainly has been used in ANNs quite a lot. It's a very mature area of research, and optimization is certainly possible using stochastic gradient descent. The difference in case of a spiking neuron is that when we calculate the gradients for backpropagation, the gradients are discontinuous, and the signals are discontinuous, and hence we may not have gradients. And hence what you really have to do is you have to come up with some approximations or surrogate gradient techniques to do the backpropagation. And that's possibly what we're going to be doing in most of those backpropagated SNNs. So with that in mind, the 3 research fronts on spiking neural networks that we're looking at are energy efficiency. And we'll see that the energy efficiency really comes from sparsity. The spikes are sparse in nature, and due to that sparse nature of spikes, one can potentially think of an event-driven hardware what one can design, and that event-driven hardware can potentially give you a good amount of energy efficiency. Second, we'll see that also in case of an ANN or a standard artificial neural networks, when we're doing computations, we do them, multiply and accumulate. Whereas in case of a spiking neuron, what we end up doing is just the accumulation. And accumulation certainly is more energy efficient than multiply and accumulate. Going further, what also one can do, and as I mentioned, one can use stochastic neurons, and stochasticity will see an important role in weight efficiency, and to be able to actually come up with weight efficient neural networks which are also energy efficient. And finally, we'll also talk about some temporality in the spike domain, where as opposed to ANNs, which does not use any timing information. In an SNN, spikes are distributed over time in some ways. So potentially, if we can use the temporal information effectively, we can build efficient dynamical systems, as we'll see. And in particular, we look at motion estimation and optical flows, and that can be quite efficient. Those can be quite efficiently implemented using spiking neural networks. So with that in mind, let me get started with sparsity, and in particular, how to train large-scale neural networks. So training of spiking neural networks. So the question, how do we efficiently train spiking neural networks? In this particular case, we're going to be using integrate and fire neurons. The coding for the inputs are going to be rate-coded inputs, and we're going to use backpropagation, as we'll see, for training of these neural networks. In the recent past, in the last 3 or 4 years, there's a good amount of progress that has been made in training these large-scale deep neural networks. The first technique, and which is the easiest one, turns out is to really take an ANN, which is a standard neural network, the deep neural network, and you take that trained neural network, don't change the weights. What you do is you actually take it and convert it into an ANN by just applying rate-coded inputs, which and rate coding has some similarity with the ReLU neurons. So that conversion works well. But the thing that you also need to do is each neuron now has to have a threshold, right? Because since we're using integrate and fire neurons, each neuron has to have a threshold. So assigning the threshold, and I'm not going to go into the details of it, that becomes quite important. If your threshold is too low, then you can have a lot of spikes going in and you're not going to learn. If the threshold is too high, there's going to be very few spikes, and again, you're not going to be learning. So the idea is to properly balance the threshold so that you get the right kind of spiking activities. So the good thing about this approach is, the pros of this approach, it can take advantage of the standard ANN training. The cons are it incurs high inference latency, as we'll see. And again, the number of time steps required to do inference can be quite large. And what we found is that we could now train, for example, CFAR10, CFAR100, or ImageNet on these, let's say VGG16 or a ResNet kind of architecture with accuracy comparable to that you would achieve for an ANN. Again, remember that since we are transferring from an ANN to an SNN, you're somewhat limited to the kind of accuracy that you can achieve. But again, the accuracy that we achieved in this particular case is comparable. And the number of time steps required is of the order about 500 to 2000 time steps. So again, the latency is large. So the question is, how can you reduce that latency? So one way of reducing the latency, and the primary reason why the latency goes up in this particular case, is the fact that there was no particular way that the latency could be, we did have latency in our training algorithm. So to that effect, it turns out backpropagation is a better way of training these spiking neural networks. And the The good thing about training using backpropagation, as I said, there has to be some modifications made compared to the standard ANN training. In this particular case, we'll be using a surrogate gradient-based backpropagation. So the pros about this approach is that you certainly get a comparable accuracy. The accuracy is quite good. And you actually end up having a lower inference latency compared to what I showed earlier. But unfortunately, the training time is high. And the reason why the training time is high is because it's a spiking network and your inputs are represented in terms of time steps. And so in other words, what you have to do is, in order to train these networks, you have to unroll the network in time, and that is quite time consuming. And hence, one can potentially apply to smaller scale networks or data sets. And in this particular case, we applied to CFAR10. And again, the accuracy turns out to be quite good. And the computational efficiency in this particular case compared to the previous case is about 6 to 15 times better. Now, the problem, difficult to apply to large-scale data sets like ImageNet. So can we do better? Of course, the best way to do that would be to really have a hybrid technique where we actually do a ANN to SNN conversion followed by some backpropagation. So this technique then is going to be really a conversion-based technique plus spike-based backpropagation. And so the basic idea, again, you do the ANN to SNN conversion with a threshold, assigning a threshold, and then you do a few epochs of backpropagation to update the weights better. And to that effect, the pros of these approaches is a faster training and more efficient training in this particular case. Now you can apply to ImageNet kind of applications, and but still the cons are still requires offline training. So it turns out that you can apply to VGG16 or ResNets, and what we found is that the number of time steps in this particular case has gone down from 2,000 time steps to about 100 to 250 for ImageNet. Of course, we need to do better. The number of time steps is still large. So the next thing that we wanted to look at, and we looked at, is what we call diet SNN. Diet because it now uses a lot less number of time steps. And in this particular case, actually, we ended up doing direct input coding. So what is direct input coding? In this particular case, we're not changing our inputs or the pixels into a rate-coded input or a time-based coded input. We are just basically directly using the input coding and using the first layer of the neural network to actually use as a spike coder, so to say. The kind of things that we're using here in this particular case is a leaky integrate and fire neuron as opposed to an integrate and fire neuron that we used earlier, and we still use backpropagation. What we found is that the number of time steps required is going to be much, much lower in this particular case. It also has much higher sparsity, and we'll see later on that we actually get much better energy efficiency. So what are the differences between the other techniques other than the direct input encoding that we're using? We're also computing the gradients for leak and threshold along with weights during backpropagation. So in other words, now the training involves not only weight updates, but also we are actually using leak and threshold as a training parameter. So going into a little more details of it, just to see how it works. As I mentioned, the inputs are directly coming from analog pixel values. And the first layer of this neural network is really acting as a spike generator. Or in other words, instead of employing Poisson-generated spike trains that we had earlier, we train an encoding layer of this neural network to convert the analog values that are coming in from the pixels into spikes. So it basically comes within the training. And of course, then that goes into the spiking neural network. So just to understand what we do in this particular case a little bit more, the training methodology. On the left, I'm basically, starting point is I'm still using a trained ANN. And the reason I'm using that is that turns out to be a good starting point. And then we do an ANN to SNN conversion as we have done earlier. And after that, what we really do is spike-based backpropagation, with direct where we are training the threshold and the leak parameters along with the weights with this back propagation, and that it turns out is quite effective in achieving a really efficient neural network. And just to compare it with these other techniques, again, the classification accuracy and energy efficiency that we get with the diet SNN. We looked at ImageNet as the data set, and the starting point, as I said, is going to be an ANN, a trained ANN that we looked at. Two kinds of architectures, a ResNet 34 and a VGG16. And then, if we look at the ANN to SNN conversion technique that I talked about earlier, you need a good number of time steps in this particular case, and again, about 2,000 to 2,500 time steps for ImageNet kind of applications. It's a large latency. Now, if I just use only 250 time steps instead of 2,500, we have a little bit of reduction in accuracy. Then if we use a hybrid training technique, as I mentioned, with some sort of back propagation along with the ANN to SNN conversion, we can get back some of these accuracy for these data sets. And then finally, if I'm just comparing with the diet SNN, in this particular case, the things are actually quite interesting. As you can see that we have accuracy which is comparable to the SNN accuracy. You can certainly get better by doing better hyperparameter optimizations. But most importantly, what we found is that the number of time steps required is only 5. So compared to a standard ANN to SNN conversion, the improvement is quite dramatic. It's about 500x compared to the standard conversions that we looked at earlier. What kind of improvement that we get in terms of energy efficiency? And again, the number of spikes is low. And again, since the number of time steps is also low, what we found is that the energy efficiency that we get from the compute point of view is again about 6 to 18x compared to an ANN. Again, we didn't look at in this particular case the power consumption, the energy efficiency coming from the memory. We are actually including memory in our analysis in the future analysis that we're doing. A few other types of coding that you can also do. It's called temporal coding or temporal switch coding that we used. So the basic idea in such a coding is that the inputs in this particular case coming from pixels of the image is represented by 2 spikes. One is a positive spike and the other is a negative spike. Yeah? And the time difference between the positive and the negative spike is proportional to the pixel intensity, as an example. And so in other words, the starting point of the pixel is given by a positive spike, and the end point is using a negative spike, or vice versa. So our TSC neuron in this particular case is also going to be a little bit different. And if we look at the membrane potential of this neuron, since we have both positive spikes and negative spikes, and if I assign a threshold, so when the input goes beyond a threshold, then a spike occurs. The membrane potential goes beyond a certain point, the spike occurs. And in fact, when the membrane potential goes down beyond that threshold, again, I generate a negative spike. So how do we train this network? And again, we used in this particular case a conversion-based training, as we have done earlier. Again, that's a good starting point. And of course, any of these conversion-based training that we do, it has to be followed by assigning a threshold, and that we do in this particular case, the threshold assignment. And what we found in this the good thing about this approach is the fact that the maximum number of spikes that you're going to have per neuron is 2. So we looked at, again, this TSC-SNN, and what we found is that still the number of time steps required is of the order of about 500 to 700. But the accuracy certainly is comparable to the accuracy of the standard ANNs that we can get. But the number of time steps is certainly larger than the diet SNN that we looked at. Going a little bit further, what we want to look at is the effectiveness of these spiking neural networks, especially for when we have looking at recurrent networks or looking at LSTMs. One thing I want to mention is the fact that if we look at a spiking neural network, the neurons do have a membrane potential, and over time the membrane potential changes, and that membrane potential certainly stored in each of those neurons. So if we think about it, the neurons really have a sequential act as a sequential storage element. The storage element certainly is not it can store analog values in this particular case. And so this itself is sort of like a recurrent neural network, but certainly not able to do the functionalities that we'd have for example, in LSTM and so on. So what we wanted to do is look at LSTMs and see if we can use spike-based computation. Now, one of the things that I'm showing LSTM architecture on the right, you directly right away see that the fully connected layers can certainly be spike-based. However, there are other functions like the forget gates and other gates that are there in that LSTM. And there are functions that you need to have, like a sigmoid-like function or a tanh-like function that you need to do. And then those need to be updated for using it or converted so that it can be used in a spiking networks. And that's exactly what we do. We propose activation functions to enable LSTM to hybrid LSTM conversion. And we evaluate the impact of this conversion to hybrid LSTM on accuracy of sequential digit recognition tasks and also sequence-to-sequence language translation. What we also did is we ended up implementing it on the Intel Loihi processor, especially the first one, which is the sequential digit recognition. We had a harder time implementing this entire one into the Loihi environment for a sequence-to-sequence energy language translation, but we actually estimated the energy improvement that we might get. So to that effect, the results on an implementation on a Loihi, hybrid LSTM on the Intel Loihi shows about 55x energy improvement for sequential digit recognition over the baseline on Intel i7 processor with less than 1% drop in accuracy. And for language translation, we estimated, and that's an estimate, it's about 3.38x improvement reduction in active energy with minimal loss in BLUE score. BLUE score is a loss that you look at when you are doing language translation, for an example. And in this particular case, we looked at the language translation from German to English. Going a little bit further and looking at stochasticity, changing gear to looking at stochasticity and weight efficiency. What we looked at, a stochastic training with, in this particular case, which we also looked at, is localized training. And the localized training, remember, I talked about spike timing dependent plasticity. So in this particular case, we're going to be looking at STDP, in particular, actually stochastic STDP for training. And since stochastic STDP based training is unsupervised, what it does is it actually ends up doing a good job of clustering. And then you certainly need a little bit of backpropagation, as we'll see, for assigning labels to those clusters. So the problem statement one can look at is, can we use stochasticity for memory efficient training? And for this training, what we did is we used a stochastic or localized learning like stochastic STDP with leaky integrated fire or a stochastic neuron with binary weights. So this shows basically an example of a network with the convolutional layers and for feature extractors. And what we also found is that it was actually difficult to use large-scale networks for STDP-based learning. It turns out it actually works well for about 2 to 3 convolutional layers. So it can be useful for probably not very complex data sets. But the basic idea in this particular case is that we had Poisson spike generators, which are input spikes coming in, and when the spikes propagates to the output of a neuron and the neuron fires, there's an output spike map which is generated, and based on this output and the input spike map, what we do is we update the weights using STDP based training. And I talked about that STDP training earlier. We made some modifications to that STDP training, which has both, in this particular case, we have Hebbian potentiation, but also we use some Hebbian and anti-Hebbian depression. So I'm not going to go into the details of it. If you're interested, I can refer you to that paper. But that kind of learning, what we found is that we can actually get reasonable accuracy. Now, few things which are important to understand is that as we have seen earlier, T pre minus T post of these neurons, the firing times, input and output, basically would lead to the difference, gives you an idea about how much the change in weight should be, or delta W. So in our case of stochastic STDP, what we did is, rather than having a change to be delta W, we made it binary, or in other words, we said, hey, it's that delta W is actually going to be a probability that that neuron switches. So rather than a delta W, we're going to use it as to be a probability of delta W. In other words, the probability that that particular neuron, or rather the synapse, should be 0 or 1, or resistance R1 or R2. As I mentioned, it actually does a good job of clustering. So beyond that, in order to actually assign labels, we actually had a couple of fully connected layers which were trained using backpropagation, and now certainly you can get the output to be to be either an animal, monument, bird, or car that we showed at the input. What kind of results we get? Okay, before I go into the results, I also wanted to mention another thing, that when we used spike-based propagation, there's vanishing spikes in the later layers of the network. And we found that it's even more important with STDP kind of learning technique. So to that effect, actually what we did is we added residual and skip connections, or residual connections, and that sort of actually makes made training easier. So with that in mind, actually what we did is we actually implemented it on MNIST. I know that MNIST is a smaller data set, but what we also did is we actually implemented in CFAR 10. It may be difficult to do it for these kind of STDP training for ImageNet kind of applications. But what we feel is that STDP based training and the kind of learning or stochastic learning that we showed here can potentially give you a huge amount of memory kernel compression. Everything is binary in this particular case. The output switching, or in fact even the weights. And what you see here is that is a good amount of kernel compression achievable with some drop in accuracy that we can find for CFAR 10. But this is actually one of those first examples where we could use CFAR 10 for some localized learning like STDP and using this stochastic STDP. We also implemented it and suitable for edge applications. So we also implemented it in silicon and showing the STDP-based learning using CMOS technology. And what we found is that in this particular case, we were able to achieve about 23 TOPS per watt for our inference. Going further, as I mentioned, that the dynamical systems are quite important, and where we'll see that the spiking neural networks do play a very, very important role. And in this particular case, we'll see that the spiking networks, because of the fact that we are going to be using timing information effectively in this case, we can get actually improvement. In fact, the accuracy in this particular case is actually better than the ANN accuracy that we actually achieved. This is actually a joint work that we did with University of Pennsylvania with Costas Denialidis' group. So what we wanted to look at is motion estimation, and in this particular, or optical flow estimation, and in this particular case, we used dynamic vision sensors. I'll go into dynamic vision sensors in just a minute, but for this optical flow, what we're really trying to do is we're looking at the displacement of the pixels over time, so which is shown on the right, and how the pixels are displaced over time, and that would actually help us in determining the optical flow. Few things which are also important to note, that we're going to be using the dynamic vision sensor cameras, and these cameras, the standard cameras suffer from motion blur, and they do not have a high dynamic range, and we'll see that these cameras are actually quite effective in taking care of motion blurs, and they do have a high dynamic range. So what is an event-based camera? So an event-based camera is basically a sensor that detects only the brightness changes, and generates spike-like outputs. So in other words, this is not going to be like the regular camera. So if I were to really look at an event camera output, it'll produce an event stream, and event camera output these asynchronous kind of events, which are basically at this microsecond resolution, and an event is generated each time a single pixel detects an intensity change. And so in other words, what we see here is that an event now is going to be represented, for example, in terms of a timestamp, the pixel coordinates, and also the sign, which is the event polarity, which basically tells you whether it's an increase or decrease of the brightness of that pixel. And so if I were to really look at an event camera and try to compare that with the standard camera output, this is an input video that I'm showing. And if I were to really look at the standard camera output, that outputs these different frames, as you can see on the top, but the devious output, which is shown on the bottom, really shows the spike outputs. And when there are no events, as you can see, it's not going to produce any output. However, when there are fast events that happens, there is a motion blur, as you can see on the top. However, the devious output is still going to be quite good in terms of these spikes. So to that effect, actually, we use these discretized input representation, which are coming directly from the cameras, which are shown as the events over time. What we did is we broke up these events into a set of former events and the latter events, into on events and also off events. And based on these two events, we actually applied to the input to a neural network. So the question is, what kind of neural network is going to be effective in terms of when we try to use it with DVS cameras for optical flow. Turns out that the spiking neural networks are going to be quite effective, that can directly take the inputs coming from the DVS cameras. And the second thing that is also important is time. In this particular case, time plays a very, very important role. And as I mentioned earlier, something which is also important is the fact that any spiking neural network sort of has an interesting property. It has an interesting property that the spikes do come in and the membrane potential goes up. So each of those neurons would end up storing this membrane potential. And then so it really acts as sort of like a recurrent neural network. So in other words, if I were to really think about implementing this architecture for optical flow detection, it does make sense to have a spiking neural network. But what we did is we actually ended up using a hybrid network architecture. So what we really mean by a hybrid neural network architecture, it has spike-based inputs coming at the beginning. And then what we found is that, remember, I talked about the fact that there is the spikes do vanish as we go further down the network. And to that effect, in order to actually take care of the vanishing spikes, we decided to use in the later part of the network to be used an ANN. So with this hybrid network in mind, we actually could get a spike flow net. The training of this spike flow net is using back propagation, using a hybrid surrogate gradient technique. So the loss, which I'm showing on the right, goes through like with a standard back propagation through this ANN block, and then we actually convert it to a surrogate gradient based method for training this SNN block. So what kind of results we get? As I mentioned earlier, that in this particular case, because of the fact that it's very well suited for spiking neural networks, what we found is that the average endpoint of error, lower the better in this particular graph that I'm showing, is better with the kind of approach that we're using compared to an ANN that was used earlier from the UPenn group. So again, the AEE, or the endpoint average endpoint error, is actually better with this hybrid network that we looked at. Finally, the computational energy benefits. We looked at the computational energy benefits by using, MACs for ANNs and accumulators for SNNs. And what we looked at is a computational energy improvement, and it turns out that the computational energy improvement is quite large. However, again, as I said, we did not include the memory in this analysis. This is an example of a demo where my student is walking in front of the camera, and as you can see, who is showing the predicted flow output and also the mask predicted flow. And what we found is that it actually, does a pretty good job. Interestingly, my student did all kinds of things, running, sort of dancing in some ways in front of the camera, and to see what kind of behavior the predicted outflow and the flow output is. What we also wanted to see is that even these event-based gesture recognition, or rather the event-based cameras, can be used for other kinds of applications like gesture recognition. And in this particular case, rather than using the hybrid network that I talked about, we used a very, very simple LSM, which is a liquid state machine, where the neurons in this particular case are connected in a random fashion, and the core of it, the only training that is done is basically from the liquid to the output. And again, the results are kind of interesting. In this particular case, again, my student is actually commanding the drone to go up, down using the gestures. Now, as you can see, that there is a little bit of a lag when or in other words, there's a delay associated with it. And the delay basically comes from the fact that the camera, which is shown in red right here, is decoupled from the drone and also the computers. So they have to communicate and get this information all in order. So again, going left, going right, you can do that with these in a very energy efficient way with these cameras. I know that I'm sort of almost out of time, but I also just quickly wanted to mention the fact that, so far I've talked about various training and inference techniques using, spiking neural networks, using different kinds of input coding. And the basic reason, the basic idea is to get energy efficiency improvement. And as we've also seen in some cases, because of effectively using the timing information, we can actually get better accuracy compared to ANNs. But all these are going to be possible. The energy efficiency is going to be possible provided you use the right kind of architecture and the right kind of devices. Now, the device part of it certainly can be implemented in CMOS, but I thought that I'll just quickly talk about the fact that the GPUs are not suitable for implementations of these spiking neural networks. You need a right kind of architecture. As a part of CBRIC and working jointly with Ascent Center, we are also looking at various kinds of emerging devices that includes, for example, ferroelectric FETs to RRAMs, PCMs, and magnetic tunnel junctions, and so on. I'm not showing CMOS right here, but CMOS is something that we're also looking at quite actively. So what I wanted to mention is the fact that as a part of our work on the architecture, we've been looking at crossbar-based computing, where you can actually implement efficiently the MAC operations, or in other words, also the accumulation operations can be implemented. And so I'm basically showing an architecture that we've been looking at. It's very similar to the Puma architecture that we have developed for ANNs. And again, this is a crossbar that we're looking at with different kinds of devices. By the way, we can also use CMOS as one of the technologies for crossbars. Again, the size of the crossbar is going to be quite larger when we use a CMOS technology. Since these crossbars have inputs which are coming digital and the outputs are analog in nature, you need some sort of analog to digital converters. And based on these analog to converters, one can actually come up with an architecture where all these crossbars that can be connected together using an SoC that I'm shown there, and these are basically the peripherals of each of those crossbars, which are A to D converters. This is a spatial architecture one can look at, and I'm not going to the details of this architecture. It's very similar to Puma. I mean, again, if you're interested, I can refer you to that. There's a GitHub. There's a you can actually try out that architecture. It's a spatial architecture with spatial scalability. And as I mentioned, one of the few things which is important is that it has a crossbar of this different kinds of devices. Could be RRAMs, could be PC RAMs, or it could even be the STT devices. The threshold functionality of the neurons can be CMOS, or it could be one of these devices like PCMs or STT MRAM devices. The motivation of using this technology is to use reasonably large crossbars, and these if the crossbars are large, then we can efficiently amortize the ADC overhead, because the ADC overhead, it turns out, for these crossbars can be quite dominant, both in terms of area and energy for these architectures. So to that effect, what we really wanted to do is to reduce the crossbar energy, and for this architecture, we needed to do something. We wanted to use large crossbars and use low complexity ADCs. And so to that effect, we need to do, for example, sparsity in the crossbar. Sparsity does allow us to use low complexity ADCs. And we also had to do device optimization so that we can get the right kind of R on to R off ratio, so that you can use larger crossbars. So with that in mind, what we did is looked at spiking neural networks, and the spiking networks have more sparsity than their corresponding ANN counterparts. And so that led us to actually optimize our crossbars better. So what I'm really showing here is that even with a magnetic tunnel junction, which may not have a high R on to off ratio, by properly optimizing it, having a thicker oxide, what one can do is one can certainly have a TMR of about 500 to 600, and that lets us use, along with sparsity, a larger crossbar size of the order of about 128 cross 128. We're also looking at ANN2, both SNN hardwares and ANN hardware in CMOS. I'm not going to be going into the details of it, but one of the things to note is the fact that in case of ANNs, we need to store, for example, the input weights and the output weights. But along with that, for an SNN, there's a need to also think about the VMEM, or the membrane potential. So the architecture is really going to consider the membrane potentials along with sparsity in order to be actually efficient. So with that in mind, I'm going to stop because I'm sort of running out of time. So in summary, going over what I talked today, we looked at different kinds of training techniques, included ANN to SNN conversions and back propagations in SNN, using also the diet approach and different kinds of input coding that we looked at. And what we found is that it's possible to get energy efficiency improvement over ANN, and that's certainly a good reason why one can potentially use in the future, spiking neural networks. I also believe that there's a lot more work to be done to really make them, suitable for the applications. We also looked at different kinds of localized learning, like STDP and stochastic STDP-based learning, which gives us a good amount of improvement in energy and suitable for, I would say, applications which are, edge intelligence, where you can do unsupervised learning. And I also believe that, again, ImageNet is not everything. It can certainly implement, reasonable tasks like CFAR10 and so on. Going a little bit further, we also looked at liquid state machines and these hybrid networks to do, for example, optical flows and also gesture recognition and so on. And I believe that SNNs are very well suited for that. And these are kind of like universal architectures that even can potentially capture multimodal dependencies. So to finally answer the question, where do SNNs fit? I feel that energy efficiency is the primary advantage at this point. Learning, and using timing information effectively can be very interesting and can potentially give better, accuracy compared to ANNs. And there's potential for edge computing, especially with, optical flows and depth estimation and so on in, for example, a drone kind of environment with DVS cameras. I personally believe that temporal domain is certainly the key, and there's a need to think about how we effectively use the temporal statistics in the best way for SNNs. I don't mean to say that SNNs are be all end. There's a lot more work to be done, but what I feel is that there are certainly interesting advantages for certain kinds of applications. And to that effect, I also believe that algorithm hardware co-design guided by biological principles can certainly be a pathway for the next generation neural computing. So with that, I'll stop. I've taken a little an hour, but I'll be happy to take any questions.